Introduction to Statistics, Chapter 12, Inferences on Categorical Data, Section 12.1, Goodness of Fit Test. The goodness of fit test uses the chi-square distribution. Characteristics of the chi-square distribution are: 1. It is not symmetric. 2. Its shape depends on the degrees of freedom. 3. As the number of degrees of freedom increases, it becomes more symmetric. The values of the chi-square are non-negative. That is, the values of chi-square are greater than or equal to 0. A goodness of fit test is an inferential procedure used to determine whether a frequency distribution follows a specific distribution. So for the null hypothesis, we let H naught be frequency distribution follows a given distribution. The alternate hypothesis will be frequency distribution does not follow the given distribution. And these two, the null and alternate, are basically the same for every problem. You might state what the distribution is, but other than that, it is the null hypothesis frequency follows the given distribution, and the alternate is frequency distribution does not follow the given distribution. Expected counts. Suppose there are n independent trials of an experiment with k greater than or equal to 3 mutually exclusive possible outcomes. Let p sub 1 represent the probability of observing the first outcome, and e sub 1 represent the expected count of the first outcome. P sub 2 represent the probability of observing the second outcome, and E sub 2 represent the expected count of the second outcome, and so on. The expected counts for each possible outcome are given by the following. Okay, E sub I is going to be the same as the mu I, which is equal to n times pi, for I equal 1 through k. Now, an example of pi, different for each category. If pi is different for each category, so if I had 4 categories here and my count is 500, if pi was 0.2, that's the probability I'm going to be in category 1. That would then be, you take 0.2 times 500, so the expected count for category 1 would be 100. For category 2, you would take 0.1 times 500 to get 50 for the expected count for category 2. Category 3, 0.45 times 500. And for category 4, 0.25 times 500. So you just take n times pi to find the count for the category. That's if all the probabilities are different. Now, what if they're the same? What if pi is the same for each category? Then we call it equally likely outcomes. Okay? If they're equally likely outcomes, then the expected count is the same for every category. So in this case, 4 categories, so that means it would be 1/4 or 0.25 of n for each case. So take 0.25 times 500, 0.2 times 500, 0.2 times 500, 0.2 times 500. So each expected count would be 125. This is if they're equally likely outcomes. So you got to realize whether the outcomes vary or they're equally likely, the probability. Now, test is for goodness of fit test. Let O sub I represent the observed counts of category I, E sub I represent the expected counts of category I, K represent the number of categories, and N represent the number of independent trials of an experiment. Then, chi squared is equal to the sum of the observed minus the expected squared divided by the expected for every category, I equal 1 through k. Now, approximately follows the chi-square distribution with k minus 1 degrees of freedom, provided that. Now, here's some things you have to keep in mind. Number 1, all expected frequencies are greater than or equal to 1. That means all EI are greater or equal to 1. Okay, so that's one thing that has to be true if you're going to run a goodness of fit test. Second, no more than 20% of the expected frequencies are less than 5. Okay, and I've noticed in some of the homeworks, they reverse this. They say more than 80% of the expected frequencies are greater than 5. So keep that in mind. No more than 20% of the expected frequencies are less than 5, or 80% of the expected frequencies are greater than 5. Now, let's go to using StatCrunch to run a goodness of fit test. This is going to be a very short chapter. You just have to understand how to use StatCrunch to run the goodness of fit test and recall everything we've talked about, whether we reject or fail to reject a test. So let me stop the show here. Okay, now here's a problem. Determine the expected count for each outcome. Over here they give us a table. They tell us n is 996, I is 1, 2, 3, 4, pi is 0.17, 0.37, 0.22, 0.24. So in this case, the probability of each category is different. So StatCrunch will not do this for you. You're going to have to use a calculator on this problem. So what you're going to do is you're going to take 0.17 times the 996, okay, with your calculator, and that should be 169.32. Okay? And then for expected count for outcome 2, you're going to take 0.37 times 996, and you should get 368.52. And for count 3, you're going to take 0.2 times 996 with your calculator, 219.12. And for outcome, expected count for outcome 4, 0.24 times 996, which is 239.04. So this is one where you're going to have to use your calculator. Okay? So now, that's one where you just find the expected counts using your calculator. Now, question 2. In this case, they want you to find the chi-square test statistic, degrees of freedom, the critical value using alpha equals 0.05, test the hypothesis at the alpha equals 0.05 level of significance. Now, they give you the null hypothesis and alternate hypothesis. Now, the null hypothesis here is that P sub A equals P sub B equals P sub C equals P sub D, which equals 1/4, which means all categories have the same probability. So PI is the same for each category. So that's the null, that they're all equal. Now, the alternate would be at least one of the proportions is different from the others. So we're going to try to prove at least one is different. Now, we have the set of data over here. This time we have the observed, we have the expected, so we don't have to calculate the expected. We can use StatCrunch now to find all this other information. So what we would do first, click on the icon, open in StatCrunch. Now, once we're in StatCrunch, you have the outcome, you have the observed, you have the expected. We're going to go under the Stat button. This time, we're doing a goodness of fit chi-square test. Okay, there's only two things you need to do here. You need to know where the observed values are. So if you drop this down, you have observed or expected. So we want to pick observed. Okay, the expected would be in the expected column. And then we can just hit compute. Now, when we hit compute, you notice the expected values are listed here, and the observed values. Now the chi-square is going to be your critical test statistic. The p-value is here. Degrees of freedom is here. N is here. That's your count. So for this first part, we wanted the test statistic. So it's going to be 1.42 because it says type an exact answer. So it's 1.42, enter. Okay. Now degrees of freedom. So if I go back, degrees of freedom was 3. That's going to be the number of categories minus 1. So we had A, B, C, D, 4 categories. 4 minus 1 is 3. Or you can get it right from StatCrunch. Now the critical value. to find the critical value. Okay, now we need to understand this alpha, and they do not, usually they give us the table to go to here. They did not give us the table to go to here. So the critical value, we're going to have to realize, okay, I'm going to have to go under StatCrunch. Usually they give you a table. I don't know why the table didn't show up there. Under stat calculators, and we'll go down to the chi-square calculator. Okay. Now, degrees of freedom for our problem was 3. So I'm going to put degrees of freedom in 3. Now, in this case, we're going to say greater than or equal, and the area is the alpha, which is 0.05. And if I compute, I get 7.814, and they wanted it to 3 decimal places, so 7.815. Okay, so usually they give you the table. In this case, you had to go to the calculator. The next problems will see the table. Should the null hypothesis be rejected? Well, this is where you look at your test statistic and your critical value. Okay, remember, the chi-square starts at 0 and goes out. So, is the test statistic 1.42 to the right of 7.815 or to the left? Well, in this case, it's to the left. It's less than the chi-square. So, since it's less than, we are not going to reject, because the critical region is when you're greater than. This is always a right-tailed test. Goodness of fit is always a right-tailed test. So no, because chi-square naught is less than or equal to chi-squared of 0.05. So we're not going to. All right. Next question. Now here, see, here is the chi-square distribution table that I thought we would have had last time, because we could have looked up in it where we could have had degrees of freedom was 3. If you look here, 3, and the area in the right tail was 5%. If you come down here, you get your 7.815. So we wouldn't have to go through the calculator if we had this table. Okay? So now let's go to our problem. We want to run a chi-square test on this problem. The null hypothesis of random variable x is a binomial with n equal 4, p equals 0.8. We're trying to prove the random variable is not a binomial with this. Okay, so it follows a different distribution. So we, over here in our table, we have observed and we have expected. So if I load this in StatCrunch, now let me shrink this down and pin it to the left. And then this is pinned to the right. Okay. Now, what I'm going to do is I'm going to do stat, goodness of fit, chi-square. Observed, expected. Click compute. Now, the first thing I want is the chi-square. So here's the chi-square, and I want it 2 decimal places. So it's going to be 14.03. Then there are how many degrees of freedom? Well, if you count here, there's 1, 2, 3, 4, 5 categories. 5 minus 1 is 4. Or if you look over here in StatCrunch, degrees of freedom was 4. Check our answer. Now the p-value. Now this time the p-value is given over here. But the way, they're not going to have you just put the p-value in. They're going to have you choose one of these 5 items here. So we got to look at our p-value, 0.072. So 0.072. Is it between? No, it's not between there. Is it less than this? No, it's not less. Is it between these? No. Between these? No. Greater than 0? Yes. So it's greater than. So this is a little trickier than just putting the p-value in. Oh. The p-value. Let me look back over here. 0072. Zero zero 7 2. This would be 500. This would be 250. So we got to go 3 decimal places here at least. So it's between, this would be 0 100 now. It's not less than that. Between, yeah, so here's the one. It's between these two. So this is going to be a little trickier than just putting the thing in. Okay, I looked at it wrong the first time. I'm sure you will too. And now, what is the conclusion at the test of alpha 0.05? Again, we do what we've always done. Look at the p-value. If it's less than alpha, you reject. If it's greater than alpha, you fail to reject. So this is definitely less than 0.05. So we're going to reject because the p-value is less than the alpha 0.05. So that means what? Since we reject, there is enough evidence in the data. And we check our answer. Okay? Next question. Now, they give you a problem here to read. So it says a manufacturer of colored candy states that 13% of the candies in the bag should be brown, 14% yellow, 13% red, 24% blue, 20% orange, and 16% green. A student randomly selected a bag of colored candies. He counted the number of candies of each color and obtained the results as shown in the table. Test whether the bag of colored candies follows the distribution stated above at alpha equals 0.05 level of significance. Using the level of significance, alpha equals 0.05, test whether the color distribution is the same. So the first thing I want you to do is choose the null and alternate hypothesis. Remember, we first assume that it takes on the original distribution. Then we try to prove it's different. So the null, let's look at this. The distribution of colors is at least as uniform as this. Now, it has to be exactly. The distribution of colors is not this now. The distribution of colors is the same as stated by the manufacturer. So that works. And then what are we trying to prove? The distribution of colors is not the same as stated by the manufacturer. So we're going to go with C this time. Okay, now, here they want the expected count. But we can use StatCrunch this time. Because if you go into the table, here's the table of colors, the frequency. If you open up the table, now we have the frequency would be the observed and the claimed proportion. So we're going to go goodness of fit, chi-square. We're going to pick frequency, and we're going to pick claimed proportion. Click compute. Now you notice here's all your expected values. So now I can just start putting them in. So let me shrink this down. Put it back over here on the left side. Get my StatCrunch. So now I can put the colors in 50.7 and 54.6. 50.7, 93.6, 78, and the last one 62.4. Check my answers. Okay, so I took care of that part. Now, the next thing, the test statistic. Well, we go back over here to what we were in. Test statistic here is going to be 16.729266, and we want 3 decimal places. So 16.729. And we go on. What is the range of the p-values of the test? Again, they want the range. So the p-value is 0.005. So again, they give us 5 things to choose from. So we got to decide which one of these it would be in. So since this over here is 3 decimal places, we should make all of this 3 decimal places. So if we make the first one 3, this would be 50, and this would be 100. So it's not between 50 and 100. This would be 10. This would be 10, and this would be 25. So this would not be between 10 and 25. Less than 0.01. Well, yes, it's less than 0.01. Greater than this? No. Between this? No. So it looks like it's going to be this one. Let's see. We got it right this time. Okay, so that's going to be trickier than just putting the p-value in. And now, based on the results, do the colors follow the same distribution as stated in the problem? Well, if we look up here, the p-value was less than the alpha. We were given alpha 0, so we're going to reject. So we look at the to reject. Now, what's it mean? If we reject, there is sufficient evidence. Not is not. So it's going to be is sufficient evidence. So now we're good. Okay. And that gave us some problems to look at using StatCrunch. And that's basically how you'll have to use StatCrunch. So I went through some of it. You may need to go back through some more of it at times. And that basically brings us to the end of section 12.1.